Welcome back everyone to 11.10 Taylor and Maclaurin Series. Now in the last video we went ahead and we actually used this idea of a Maclaurin polynomial. We calculated one of degree 2, but I haven't told you what this thing is. So I'd like to start with that. Let's get to it. So in the case of Taylor series, the partial sums are these t sub n's. So we need a new variable. I'm going to use I, which is going to range from 0 now to n, which is this maximum degree. And then everything else is the same. So we're going to take the ith derivative of f, evaluated at a, divided by I factorial times x minus a raised to the ith power. All right, so it should look, again, pretty much the same. So f of a plus f prime at a divided by 1 factorial times x minus a plus so on and so forth. But now we stop, right? We have a maximum degree here, which is n. So this is the nth derivative of f at a divided by n factorial times x minus a to the nth power. So this is an nth degree Taylor polynomial, right? So the main thing is to notice that t sub n is a polynomial of degree n. So, like I just said, this is the nth degree Taylor polynomial of f at a. Now, obviously, if you change f or if you change a or things like this, you'll get different polynomials. And now the claim is we've already essentially seen this. Back in our previous example, we found a Maclaurin polynomial, right? So we stopped at degree 2. So this would be nth degree. So we would just stop at degree n, whatever n is. Now in general, if you want Taylor series, you can build this from Taylor polynomials. And the way that you do this is that you take the limit as n goes to infinity of our partial sums, right? Our nth degree Taylor polynomials. Okay, and the last thing is how well does this do, I guess, of approximating the function. So we're going to talk a little bit about a remainder, which is this r sub n thing. R sub n of x, which we're going to define to be just f of x, the function itself, minus the nth degree Taylor polynomial. So that way, really, f of x is equal to the nth degree Taylor polynomial plus this r sub n at x. So again, this r sub n at x is called a remainder of the Taylor series. So this is whatever's left over. This is how far we are away from the actual function. All right, so we'll do some computing of remainders a little bit later on. For now, though, let's try to find a Taylor series generated by f of x equals 1 over x, centered at now a equals 2. So this is very similar to what we did originally, but now we're centering at a equals 2 instead of a equals 1, and we want the entire series. So we don't want to just stop at 2 or 3 or something like this, but we want to go on forever. So the claim is that there's some new challenges that this brings up. So I'd like to talk to you a little bit about those. So, okay. Using our coefficient formula, we know that we need to calculate out a lot of derivatives, and we need to evaluate at 2. So again, let's remind ourselves, Taylor series is the sum from n equals 0 to infinity of c sub n times x minus 2 now raised to the nth power, where these c sub n's are given by the nth derivative of f at 2 divided by n factorial. So like I just said, we need to calculate out a lot of derivatives. We need to try to figure out, in general, what does the nth derivative of f actually look like? And in order to do this, I like to calculate out the first few by hand and then kind of expand from there. So, okay, the original function, 1 over x. If I take the derivative, I get negative x to the negative 2. Take a second derivative, I'm going to get, well, this is going to be negative 2 comes down, there was a negative 1 in front, times x to the negative 3rd power. If I take 3 derivatives, we're going to have negative 3 times negative 2 times negative 1 times x to the negative 4. And so my hint to you is to not simplify at all. This will give us a better idea of the pattern. So don't simplify. Okay, when I plug in 2, and again, I'll do this to the derivative, the second derivative, and the third derivative, and then eventually I want to expand on this to get the nth derivative of f at 2, right? I need some formula here that depends on n. So again, I'm getting a running start, trying to figure out what these things are going to look like, and then I'm going to generalize. So if I plug in 2, well, I would just get 2 to the negative 1. Okay. How about if I was to plug this into the derivative? Well, I would have this negative 1 times 2 to the negative 2. The second derivative, I would have negative 2 times negative 1 times 2 to the negative third power. And while I'm doing this, I'm already seeing some patterns, right? So you can first of all notice that we have this 3 times 2 times 1 in the third derivative, or 2 times 1 in the second derivative, right? So it always has to do with how many derivatives there are. That's kind of your highest number, your lowest negative number. Okay, so I'm going to need to propose a general formula. I want to remind myself here I have n equals 0, n equals 1, n equals 2, n equals 3, and now I need the general case. Okay, so maybe I'll start with these powers of 2, right? So the powers of 2, they start at negative 1, then go negative 2, then go negative 3, then go negative 4. So it's like 2 raised to the negative n plus 1, right? It's negative, but it's always 1 higher than the value of n, right? So at n equals 3, for instance, we have to the negative 4. Okay, so I think I'm happy with this. And then the next thing is that I see that there's this alternation, right? It goes positive, negative, positive, negative. So in order to get this, I'm going to do a negative 1 to the nth power. And then we can see, first of all, at 0, we would have positive. At 1, we'd have negative. At 2, we'd have positive. At 3, we'd have negative. Perfect. And then finally, there's this whole 3 times 2 times 1, 2 times 1, 1, and then technically there's a 1 out in front here. So this has something to do with like a factorial, right? I've already taken all of the negative stuff. I have the negative information already, but this has something to do with like a factorial. So it looks like it matches up exactly with n, right? Because when n equals 3, we'd have 3 times 2 times 1. When n equals 2, I have 2 times 1. And when n equals 1, I'd have 1 factorial. And then technically 0 factorial is indeed 1. So my proposal is that this is a formula for the nth derivative of f at 2. And we can see that we have all three components. They all match up perfectly. So yeah, I'm happy with this. So our last step is to go ahead and plug this into our formula to get the Taylor series. So again, this is going to be the sum from n equals 0 to infinity of our c sub n's. So we now know what the derivative is, and now don't forget to divide by n factorial times x minus 2 to the n. So we have a little bit of cancellation going on here, and we get the sum from 0 to infinity of 2 to the negative n plus 1 times negative 1 to the n times x minus 2 to the n. And there we go. That is the Taylor series generated by 1 over x centered at 2. And the claim is, again, if we go back and we look at when we had a equals 1, right, this doesn't match up. So when we change the a value, you get a completely different Taylor series. Well, they're related, but they're different. Okay, so now I want to go over some important Maclaurin series. Like I said, Maclaurin come up a lot, and we've kind of crossed paths with a few of these, but I want to go ahead and give you what are the Maclaurin series for some of our common functions. So for instance, for 1 over 1 minus x, right? This is the sum from n equals 0 to infinity of x to the n. We already know this, but we can prove this actually with Maclaurin series. So one can prove this. The other thing are these radius of convergence. Now I'll show you how to prove these here in just a second, but these radius of convergence are important. They tell you how long are the series actually good for. Okay, how about e to the x? This is going to be the sum from n equals 0 to infinity of x to the n over n factorial, and this is the one that I'm actually going to prove for us here in a second. But if we expand this out, plugging in n equals 0, n equals 1, and now n equals 2, right? So x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth forever and ever and ever. And the claim is this series does a really good job everywhere, right? The radius of convergence is infinity. So great. Sine, the claim is that it looks a lot like e to the x, but we have a little bit of alternating, right? So there's this negative 1 to the n, and we only get the odd powers. So notice how close this looks to e to the x, but we're alternating, and we only have odd powers. So x cubed over 3 factorial, maybe if I plug in one more value, if I plugged in n equals 2, we would have this, let's see, positive x to the 5th over 5 factorial and so on and so forth. And again, this one does a great job. R equals infinity, so it approximates sine of x everywhere. Likewise, cosine has this alternating back and forth sort of business, right? Because it has this -1 to the n, but now it only has even powers, interestingly enough. And remember, sine is an odd function, cosine is an even function, so maybe we could have guessed something like this. So let's see, if I plug in 0, I'd get 1. If I plugged in 1, I would get -x squared over 2 factorial. If I plugged in n equals 2, I would get plus x to the 4th over 4 factorial. And I could keep going. Maybe I'll do one more here. But again, these all go on forever and ever and ever. There's infinite series. And again, this one has a quite good radius of convergence. It's r equals infinity. So it approximates cosine of x everywhere. Tangent inverse of x. Again, we can see this one has radius of convergence r equals 1, so it's not as good. This one has just odd powers of x, but notice that the denominators, we don't have these factorials anymore. And it goes on forever and ever and ever. Natural log of 1 plus x, we actually derived this one earlier in our notes. This was the integral of something like 1 over 1 minus x, so it's no coincidence that these things look very similar. We do have a negative here, and positive and negative, x to the n over n, right, which again should look quite similar to the integral of 1 over 1 minus x. Imagine if u was equal to -x. And that's why the radius of that one's going to be 1, radius of convergence. And then finally, we have 1 plus x to the k. And this is an important one. This will come up often in your homework. This is a binomial coefficient right here. This is k choose n. And so I want to tell you what the first few values of this is. So 1 plus kx, so this would be k choose 1. K choose 0 is just 1. K choose 2 is going to be k times k minus 1 over 2 factorial. K choose 3 is going to be k times k minus 1 times k minus 2 over 3 factorial. And of course, all of these have powers of x next to them. And the radius of convergence for the binomial series is 1. So let's go ahead. I've claimed that this is a theorem, right? That one can actually prove these things. You don't have to take my word for it. You don't have to memorize these things. So let's actually prove what I'm claiming here. So I want to show that the Taylor, or really Maclaurin series for e to the x is this x to the n over n factorial, summing from n equals 0 to infinity, and that the radius of convergence is infinity. So we need to calculate out some derivatives, just like we did in our last example, and then we need to expand on this and try to figure out a general formula for the nth derivative of f. In this case, it's at 0, right, because it's Maclaurin. So e to the x, first derivative is e to the x, second derivative is e to the x, third derivative is e to the x, and we can see that this is kind of straightforward. So if I plug in 0 into all of these, I get 1. So no matter what the derivative is, when I evaluate at 0, I always get 1. So you can see I kind of got the pattern here. So this is going to be the sum from n equals 0 to infinity. Now my c sub n's are supposed to be the nth derivative at f divided, at 0 divided by n factorial times x to the n. So in this case, my derivatives here are always 1. So this is 1 divided by n factorial times x to the n, which another way we could write this is just x to the n over n factorial. And now we can see our formulas match exactly. So thanks to our formulas about Maclaurin and Taylor series, we can find this. Okay, so again, you don't have to really memorize this or take my word for it. One can actually prove this. So now let's show that the radius of convergence is infinity. And the way that we're going to do this is with our good old ratio test. So we're going to take the limit as n goes to infinity of a ratio of subsequent terms. So this is my a sub n plus 1 divided by a sub n. And right, and if we want this to converge, we want to make sure that it's less than 1. So we're wondering what kind of x values could I plug in and make it less than 1. Well, let's go ahead and simplify a little bit. You can see that there's going to be an x here. And let's see, I have this 1 over n plus 1 factorial and divided by, so let's go ahead and multiply by the reciprocal. So this is going to be n factorial. And we know that n plus 1 factorial is the same thing as n plus 1 times n factorial. And now we can see a little bit of cancellation happens. Now as n gets very large, remember x is constant here. So I'm going to kind of separate this. As n gets very large, what happens to 1 over n plus 1? Well, it heads towards 0, right? And when is 0 less than 1? Which values of x? Well, you can see there are no longer x's even in this equation. So this is always true. No matter which x value you choose, it works, it converges. The ratio test is going to be less than 1. So, by the ratio test, we know that the radius of convergence is infinity. So that's how one can actually prove what the radius of convergence is. So at the beginning of 11.10, I made a promise that we were going to be able to represent a lot more functions as power series. And now you see how we do that with Maclaurin and Taylor series. All right, in the next video, I have 3 more examples for you. Take a quick break, and then let's get to it. I'll see you next time.